Perfect. So good morning, everybody. It's a great pleasure to have today Matt Kwan. Right, Matt is professor in IST, and you can read his bio together with the announcement of seminar. Right, I'm very proud to be Matt's advisor. Right, he's doing extremely great and proving excellent result. And one of them he will present today, and it's about quadratic Littlewood-Offord. Please, Matt.
Thanks for the introduction. It's also a great pleasure to be speaking at this seminar. It's a really cool initiative for sure. Yeah, so I'll be speaking about a topic called the Quadratic Littlewood-Offord problem. And this is joint work with Lisa Sauermann, who's at Bonn. I don't necessarily expect you to know what the Quadratic Littlewood-Offord problem is. And I thought instead of telling you immediately what it is, it would be good to start with some motivating questions, which we'll sort of see in a moment, turn out to be related. So the first question is a question that I have been quite fond of for some time now. It was posed by, well, it's a general class of questions that was first posed by Alon, Heffetz, Krevelevich, and Topkin. And what they asked is, if you give three numbers, k, l, and n, and let's assume that L is a possible number of edges in a graph on k vertices, so it's somewhere between 0 and k choose 2. And let's assume that n is much larger than k in some vague sense. And then you're interested in how many subsets of k vertices is it possible to have which contain exactly L edges in an n vertex graph. Okay. So clearly this number is at most n choose k. There are n choose k ways to choose a subset of k vertices. Can it be the case that all of them induce exactly L edges? Well, it's easy to see by Ramsey's theorem that's not possible, but can you show that it's somehow much smaller than that? And maybe you can prove something quantitative depending on the values of L and n and k. So this is some sense in which it's like trying to quantify the extent to which it's not possible for graphs to be really uniform. So I mean, if L was equal to 0 or k choose 2, then it would be possible that every subset has the same number of edges. Like the complete graph and the empty graph are really uniform, but maybe there's no other way to be quite so uniform. So that's one type of question. Another question is, so I've attributed this to Weiss. It's usually called Weiss's conjecture, but it's kind of a folklore question.
Actually, it's Weiss, Mathew. It's Benji Weiss. You pronounce his last name, Weiss.
Okay, Weiss it is. Sorry about that.
No problem.
So the question is, if I give you a symmetric binary random matrix, so meaning the entries, this is an n by n matrix, its entries are 0 or 1, and I just choose a symmetric matrix with 0, 1 entries uniformly at random. Or equivalently, I can flip a coin for all the entries above the diagonal and just mirror the thing below the diagonal. And then I'm interested in the probability that this matrix is singular, as in what is the probability that it is not invertible. So if you're interested in like a continuous random matrix, then with probability 1, it's going to be invertible. It's not going to be singular, just because the set of all singular matrices is like a lower dimensional subvariety. But in the discrete world, it's not quite so obvious. And so this was a conjecture. It's no longer a conjecture. It's now been proved. But this is a difficult thing to prove, the singularity probability as little O of 1. So as n goes to infinity, it becomes less and less likely that a random, in this case, symmetric matrix is singular. Okay, so these are two questions which superficially are maybe not quite that related, but what they have in common, well, one thing they have in common is that they can both be phrased as questions about anti-concentration. So they can both be phrased as a question about trying to show some random variable is not too likely to be equal to some particular value. So let me write that. So this first question here, this is, I can phrase it equivalently. So equivalently, this is asking that if I consider a random subset of k vertices, and let x be its number of edges. And then I'm interested in what is the probability that x is equal to L. And like, I'm trying to show that, you know, can I show that this is this probability is small? So this can be phrased probabilistically, and this one can also be phrased as an anti-concentration question, equivalently. I'm asking here, what is the probability that the determinant of Mn is equal to 0? Okay, so in both cases, I'm interested in understanding the probability that some type of random variable is equal to some type of value. Okay, so this is called anti-concentration. So what sorts of general tools do we have for understanding anti-concentration? So the most famous one, well, a very famous one, is something called the Littlewood-Offord theorem, which let me tell you about that. So it's a theorem, Littlewood-Offord. That morally speaking says sums of independent random variables are anti-concentrated. The probability they're equal to something is small. So let's write the statement. So let x be a1, a1 xi1 plus an xin for some coefficients a1 through in which are not equal to 0. So real numbers which are not equal to 0, and xi1 through xin, which are let's say uniform on plus minus 1. So what I mean by this is, so each of these xi's is like an independent random coin flip. It's either plus 1 or minus 1. And then I have some coefficients, a1 through an. And so this random variable x is just, it's like a random sum according to these coefficients. So each of the AIs is present with the plus 1 or minus 1, and I add them all up. That's my random variable. Then for all real numbers x, the probability that x is equal to that is bounded by a particular formula, n choose n over 2, let's say rounded down in case n is odd, divided by 2 to the n, and by Sterling's approximation, that's about 1 over square root n. Okay, so whenever you take a random variable like this, the probability that's equal to anything is vanishingly small as n tends to infinity. That is the Littlewood-Offord theorem. So some remarks I would like to make. The first one is that I've stated this for the uniform distribution on plus minus 1. This is called the Rademacher distribution, but really that wasn't essential. This holds for any distribution. So same theorem holds for any distribution of the xi. As long as they're independent, then if you fix the distribution, let n go to infinity, you get this bound. Maybe not this exact bound, but you get 1 over square root n type behavior. And also to comment on like what is the meaning of 1 over square root n. So how should I think about this? Well, I want to think of it in terms of the central limit theorem. So let's say as an observation that if so these coefficients in general, they can be very different to each other, but in the special case where they're all the same, or they're all roughly the same, if they're roughly equal to 1, then the distribution of x is by the central limit theorem roughly Gaussian with mean 0 and standard deviation square root n. And so that means that there's some region, there's some window of size square root n that this random variable is very likely to live. And because things are nice and Gaussian and smooth, we expect that every point in this region has about the same probability. And so it's not so surprising from this point of view that we should expect a bound that looks like 1 over square root n. Now, so this is actually a way to prove the Littlewood-Offord theorem if each of these coefficients are roughly the same as each other. Of course, I'm making no assumption that these AIs are the same. And in general, it could be that, for example, if these AIs increase very rapidly, if they increase exponentially fast, this distribution could be very far from Gaussian. But nonetheless, this is saying that sort of the anti-concentration behavior of the Gaussian is sort of the worst case. This is sort of a shadow of the central limit theorem that you see even when you break the IID assumption of the central limit theorem. Okay. So to remark a little bit on the history of this problem, so what really happened here is that Littlewood and Offord had proved a similar bound, but instead of 1 over square root n, they proved a bound of log n over square root n. They proved this as a tool to study random polynomials. And the way that they proved this was actually by Gaussian approximation. So they were able to break up the random variable x into sort of buckets in such a way, into log n buckets, according to sort of order of magnitude of the coefficients, in such a way that within each bucket, you can safely use Gaussian approximation. And so you can use a quantitative central limit theorem to prove a 1 over square root n bound, and then sort of just use the fact that you've got at most log n buckets to get a bound of log n over square root n. So then Erdős, a few years later, managed to come up with a completely different proof. So this bound here is really just due to Erdős. And he managed to turn this into a combinatorial problem. So he managed to study this probability that my random variable is equal to something, so that without ever directly getting his hands on what is the distribution of the random variable. And in doing so, he was able to get a very precise result. So yeah, so Erdős's proof is quite beautiful and actually very short. So I thought I would actually show it to you. So unfortunately, this isn't quite like a blackboard, so I can't have the statement on the screen at the same time as the proof. But maybe to remind you, so the statement of the Littlewood-Offord theorem is that I have some coefficients, some coin flips plus minus 1. I add up the weighted coin flips, and I'm interested in proving that the probability that x equals x is almost this. Okay, so let's prove this theorem. So the first thing is that without list of generality, I can assume that each of these coefficients is positive. And the reason is that, well, the plus minus 1 distribution of the xi's is symmetric. So if I change ai to minus ai, I actually don't change the distribution of my random variable. So this is a safe assumption. And then I'm going just to define some notation. I'll let vec a be the sequence of coefficients, and vec xi be the sequence of random variables. And I've done this so that x is nothing more than the dot product of these two. Okay, so this problem is a priori just about a single random vector psi. But the idea here is that I'm going to compare this to a sequence of random vectors, which is going to be sort of dependent with each other, and I'm going to take advantage of the dependence. So I'm going to let psi 0 be the all minus 1s vector. And I'm going to let psi I, so this is a vector, psi I be obtained from psi I minus 1 via a random -1 to 1 flip. So this is just like a random path of the Boolean hypercube. So I started the all minus 1 vector, and then to go from each step to the next, I take a random -1 and I change it to +1. So eventually, after having done n of these steps, I'll end up with a vector whose every entry is +1, and this is just a random path from -1 to +1. Okay, so why have I done this? Well, so if I let y be the number of I for which vec a dot psi I is equal to x. So remember, I'm trying to understand the probability that this dot product is equal to x. And instead, I'm going to, I've now got this evolving random vector, and I'm going to study the number of times for which my evolving random vector dot A is equal to x. Then y is always at most 1. And the reason for this is that because I'm assuming that each AI is positive, whenever I do one of these flips from -1 to 1, you know, how am I changing this dot product? Well, there used to be a minus AI, I'm changing it to a plus AI. So no matter which flip I make, I'm increasing the value of my dot product. And so if I increase the value of my dot product at every step, there can be at most one step for which I hit my target exactly. Okay. So certainly this random variable is at most 1. But on the other hand, I can compute the expected value of this random variable just by linearity of expectation, just by separately looking at each xi. So let's do that. The expected value of y, which we know is at least 1, that is the sum over all I of the probability that this vector A dot xi is equal to x. And so what is the distribution of xi? Well, there's some dependence between the different xi, but if I just look at some individual xi, it's just a random vector with exactly I ones. So that's the sum over all I of the probability that A dot xi is equal to x, given that xi has exactly I ones. So this here is just my notation for the number of ones in a random, well, in a vector with ones and minus ones. And so the point is that both, if I condition on my original random vector xi having exactly I ones, well, it's uniform over all vectors with exactly I ones by symmetry, which is the same distribution as the marginal distribution of xi. So this is true, and so by Bayes' rule, this is equal to the sum over all I of the probability that A dot xi is equal to x. And this has exactly I ones divided by the probability that I've got exactly I ones. And then I can just pull out the maximum value of the denominator. So this is at least 1 over the maximum over all I of the probability that I has exactly I ones. Times the sum over all I, the sum of the numerators. And what is the sum of the numerators? Well, I'm summing the probability that A dot xi equals x over all possibilities of the size of the number of ones in xi. So that's nothing more than, let me skip a step here. That's nothing more than the probability that A dot xi is equal to x. Okay. And because I know that the expected value of y is at least 1, because y is always at least 1. Now I can just rearrange this. Well, okay. So what is the maximum probability that I have exactly I ones? Well, this probability is precisely a binomial probability. Like the number of ones in a random plus minus 1 vector. Like I flip a coin for each entry, decide whether it's 1 or minus 1, and if I'm counting, it's just a binomial distribution. The binomial distribution is bimodal, and its maximum probability is precisely this expression that we saw before, n choose n over 2 divided by 2 to the n. This is the central binomial coefficient. And so if I rearrange this whole business, then I prove the Littlewood-Offord theorem. The probability that A dot xi is x is at most this probability, which comes out to about 1 over square root n. Any questions about this? Yeah. So I think this is a really beautiful proof, and somehow what's amazing about this proof is that it's purposely learning nothing about the random variable except what it needs to know. Like it's not doing any Gaussian approximation to understand the full distribution. It's really just trying to get its hands on this specific event of the random variable being equal to something. And this is actually quite a robust proof technique as well. So together with Jacob Fox and Lisa Sauermann, we managed to apply this type of thing to other types of random variables. Anyway, so now we know about the Littlewood-Offord theorem. It tells us that sums of independent random variables are anti-concentrated. And so now we can return to these motivating questions. Where were we? So we had this Alon Hefetz-Korolevich-Tompkin question and Weiss's question. And we can ask, can we apply this Littlewood-Offord theorem to these settings? And unfortunately, the answer sort of superficially is no, because neither of these things are sums of independent random variables. The number of edges in a random subset of vertices or the determinant of a random matrix, neither of those are can be obviously expressed as sums of independent random variables. I would like to mention that for this random matrix thing, so if I was interested not in a symmetric random matrix, but just in a random matrix with IID entries, well, then it would be possible to use the Littlewood-Offord theorem. And in fact, that's sort of one of the most famous places the Littlewood-Offord theorem has been applied. Because if I imagine, if I've got some like n by n matrix, and if it's not symmetric, if it's just got independent entries, and I expose everything except the last row of the matrix. So if I check what are the values of the entries in the first n-1 rows of the matrix, and I leave just the last row being random, well, then conditionally, what is the distribution of the determinant? Well, by minor expansion, it's like it's precisely the sort of thing you see in the Littlewood-Offord theorem. So I have a bunch of coin flips here, like psi1 through psi-n, and each one has a coefficient, namely the corresponding cofactor of the first n-1 rows. And so that's precisely the form of the Littlewood-Offord theorem. And so one needs to prove that the coefficients of this linear form are non-zero, but that's precisely how to prove that in the IID case that a random matrix is non-singular. Now I can't do that in the symmetric case because the symmetry constraint is preventing me from exposing the first n-1 rows without accidentally exposing the last row. But of course, something that I can do is say, well, let me expose everything in a matrix except the last row and the last column. So if I expose whatever's going on up here, but leave the last row and the last column, well, now this last row and this last column still have all their randomness. They have the same distribution, the last row and the last column by symmetry. But that's just still an independent sequence of coin flips. And so then, having done this, I can ask, what is the distribution of the determinant? And you can see that now, so it's not going to be a linear combination of independent random variables. It's going to be a quadratic function of independent random variables. Because, I mean, again, if you do cofactor expansion, you're going to get like some xi here and some xj here. They're going to have some coefficient depending on the corresponding minor of the matrix. Yeah. So actually, for Weiss's conjecture here, I think what we've just discovered is that what we need is not quite the Littlewood-Offord theorem, but we need a quadratic version of it. We need the same thing, but instead of linear sums of independent random variables, we need a quadratic function of independent random variables. And actually, that's exactly the same thing that's happening here. So I guess, well, so a random subset of k vertices isn't necessarily, I mean, that's not obviously determined in terms of independent choices at all. But a cheap thing you can do is say, let me first start by randomly choosing k pairs of vertices disjointly. So I choose 2k vertices, each of which is partitioned into pairs. And then for each pair, I flip a coin to decide which of the two I'm really going to take. So I can define like a two-stage exposure procedure to generate a random set of k vertices. And once I do that, I really do have a sequence of independent choices. And I can ask, in terms of those sequence of independent choices, what kind of random variable is x? And I think it's quite easy to see this is also a quadratic polynomial. The reason is that I'm interested in, well, so x is the number of edges. So for each possible edge that could be there, in order for that to be included in my random set, both endpoints of that edge need to be included. And so the event that I'm included is like a quadratic term. The product of two things has to happen. Okay. So both of these are quadratic questions. And so we would really like a quadratic version of the Littlewood-Offord theorem. And so fortunately, there is such a thing does exist. So it was proved. So it was actually independently proved. So Rosinski and Samorodnitsky proved this actually a long time ago, and I think it was forgotten a little bit. But most famously, this was proved again by Costello, Tao and Vu. So they proved a quadratic version. Okay, so these authors proved this as a technical tool in order to study something called Levy chaos. But Costello, Tao, and Vu proved this precisely in order to prove Weiss's conjecture, to prove that random symmetric matrices are typically non-singular. But the statement of what they proved is the following. So let Q be a quadratic polynomial. And so if you remember that for the Littlewood-Offord theorem, I needed to assume my coefficients were non-zero. So that business is a little bit more complicated here. And so what I'm going to assume as my non-degeneracy condition, I'm going to write such that each variable appears.
It's homogeneous, so all terms have degree 2, or you allow linear term as well?
So I think the homogeneous case encapsulates basically all the difficulties, but I want it to be true for all quadratic polynomials. So there's allowed to be a linear term and there's allowed to be a constant coefficient. Yeah. Okay, so my non-degeneracy condition, my condition that is saying sort of that I'm far from the zero polynomial, is that each variable needs to appear in at least Cn non-zero terms. Okay, so quadratic polynomials have roughly n squared possible coefficients. Each variable can appear in roughly n different terms, and I want a constant fraction of those to actually be present with non-zero coefficients. So this is a rather strong condition, and the different work on this topic has used different types of conditions, but this condition in particular is strong enough for all the work on this topic. So the statement is then that okay, so for convenience, I'm going to write the probability that Q of so 1 through xi n is equal to 0 is at most n to the minus 1/4. Okay, so here I mean these xi1, xi n are exactly the same as before. They're random coin flips. They're +1 and -1 with probability half. And here I'm interested in the probability that's equal to 0. So before I was looking at the probability that's equal to x for any x, but really it's the same question, because if I want, I can put a constant coefficient in Q. So I can, instead of studying Q, I can study Q minus x. And so this is really a bound on the probability that a quadratic polynomial is equal to anything. And yeah, so and then the bound is that this is at most n to the minus 1/4. And this was enough for Costello, Tao, and Vu to prove Weiss's conjecture, and I suppose it was enough for Rosinski and Samorodnitsky to prove whatever they were trying to prove about Levy chaos. But it doesn't quite look well. This theorem raises a few questions. The first is that this assumption here that each variable appears in at least Cn non-zero terms, that's a sort of clumsy-looking assumption. And it would be nice, like naively one might hope, is it enough just for each variable to appear somewhere in the polynomial? So I do need some assumption. The variable does need to appear with some non-zero coefficient, otherwise the variable doesn't count for anything. But maybe I just need each variable to appear somewhere. Unfortunately, that's not quite enough because I could have the polynomial Q of x being equal to x1 minus x2 times x3 plus x4 plus xn. So this is a polynomial where each of the n variables genuinely does appear and have some impact. But almost, well, with probability at least a half, it's going to be 0, because whenever x1 is equal to x2, the whole thing is equal to 0. It doesn't matter what this is. So the probability here, the probability that Q equals 0 is large. So, right. So you can't hope for a sensible conclusion. I mean, you can't hope for a probability that goes to zero without making some kind of robust assumption that each variable doesn't just appear somewhere, but appears in some robust sense. So this condition is kind of clumsy, but in some sense, it's kind of necessary. The other question is what's going on with this bound here? So there was sort of a good reason for the 1 over square root n bound in the original Littlewood-Offord problem. Like, it was the best you could hope for in the case where all the coefficients are equal, because then by Gaussian approximation, that's really what you expect. And so one observation is that you can't hope to do better than the linear case in the quadratic case, just because you could take your favorite linear polynomial and square it, and well, the probability that a square is equal to something is the same as the probability that the square is equal to the square root. So you can't hope for a bound better than 1 over square root n. But maybe I should be aiming for a bound of 1 over square root n. Maybe this is not the right bound. So this conjecture, well, that possibility was raised as a conjecture actually independently multiple times. But I think the first time was due to Nguyen and Vu. They conjectured that under this type of assumption, so when you have some sort of robustly non-zero assumption, this probability should in fact be at most 1 over the square root up to some constant. So there's been work. There's been a variety of work sort of towards this, not just for the quadratic case, but also for higher degree polynomials. Well, given that this is not, I mean, I'm not trying to be exhaustive here. Let me just mention the state of the art. Well, the state of the art prior to our work was due to Kwan. He had managed to prove that this probability, well, I mean, not read the details, is at most up to polylog factors. This is correct. So at least in the quadratic case, log n to some constant power divided by square root n. He managed to prove. Okay. And the way that he managed to prove this is actually somewhat analogous to Littlewood and Offord's original Gaussian approximation proof of the Littlewood-Offord theorem. So I recall that, so I described that one way to prove a weak bound for the Littlewood-Offord theorem is to sort of break up your linear form into pieces and do Gaussian approximation on each piece. And both of those parts are not obvious how to do in the quadratic case. It's not obvious how to break up a quadratic polynomial into pieces in a sensible way. And it's not obvious, even once you have a sensible polynomial, how to do Gaussian approximation for it. But both of these things are possible. So there is a thing called a Gaussian invariance principle, which allows you to relate a low degree polynomial of plus minus ones to a low degree polynomial of Gaussians. And there's a thing called a regularity lemma for Boolean functions, which allows you to somehow break up an arbitrary low degree polynomial into a low complexity decision tree. And by combining these together with some other very nice ideas, there's some very nice recursion that allowed him to prove a bound like log n over square root n. It does seem like with this sort of approach, you tend to lose log factors. Perhaps one immediate reason why one should expect this sort of thing is that if you're going to do some kind of Gaussian approximation, you care about what the value of the coefficients is, like what the size of the coefficients is. And so if you want things to be nice and well behaved, you expect to need to do some sort of dyadic partitioning to break things up into logarithmically many scales, if you want things to sort of be nice and constant on each of your pieces. But somehow this, this is the sort of thing you need for Gaussian approximation. You need log n scales, but we're not really interested in Gaussian approximation here. We just want to understand the probability that a quadratic polynomial is equal to something. And so we shouldn't really care about sort of sizes of coefficients. And ideally, there should be some proof resembling the Erdős's proof, which is sort of more combinatorial and sort of more directly gets at the event that I'm interested in, rather than trying to actually understand the entire distribution of my random variable. And so this is the new result that I would like to share today. So together with Lisa Sauermann, we proved, so we managed to prove this conjecture, but under a slightly different assumption. So I'm going to write probabilities at most 1 over square root s, assuming it is not possible to reduce q of x to a constant polynomial by fixing the values of s variables. So this is a strengthening of the Nguyen and Vu conjecture. Let me just talk a little bit about this this assumption here. So remember, the issue here with this quadratic polynomial, the reason we were not getting good anti-concentration here is that when x1 is equal to x2, the whole thing is equal to 0. So there's some way to just fix x1 and x2 and sort of collapse everything down to a constant. And what this theorem is saying is that that's sort of the only thing that can go wrong. So if there's some way to fix the values of a constant number of coefficients in order to make the whole thing constant, well, you're out of luck. You can't prove good anti-concentration. But you can prove good anti-concentration as a function of the minimum number of coefficients you need to do that. So if you would need to fix at least s coefficients to fix the value of the polynomial, you get a bound of 1 over square root s. So this assumption here, that each variable appears in at least Cn non-zero terms, it is easy to see that if you have that assumption, well, then it is not possible to fix fewer than some constant times n variables and thereby fix the value of the polynomial. The reason is just that this assumption means you have quadratically many non-zero terms. And so it's like imagine that you have like a graph with quadratically many edges. You must have a matching of linear size, and you can't pin the matching with fewer than linear by fixing fewer than linearly many variables. Yeah. So this strengthens the assumption. Well, it's a weaker assumption, therefore a stronger theorem, including so the various assumptions will be considered in various various previous work, but this is so this theorem strengthens all these assumptions.
Matt, so can I ask you, so you mentioned that Kane works for any degree polynomial, so this also generalizes?
So I'll talk about that a bit later on. So I'm going to describe a general strategy for you in a second. So we think the strategy makes sense in general. It's a robust strategy, but there are some difficulties in generalizing it to arbitrary degrees. So this is really just a theorem about quadratic polynomials. But we hope that this technique will open the door to prove all sorts of things about polynomial Littlewood-Offord problems. So, yeah. So perhaps, sorry, did you say something?
Yeah.
So perhaps let me tell you about how we prove this, and then this aspect should become clear. So I can't tell you about our new ideas without telling you about Costello, Tao and Vu's ideas, which were actually the same as Rosinski and Samorodnitsky's original ideas. It's a technique called decoupling, which is a sort of ambiguous word that means different things to different people. But here's what I mean by it here. So I'm going to write I to be 1 through n over 2, and j to be n over 2 plus 1 through n. So I have n variables, n indices in my original problem, but I'm going to break that up into 2 parts. And I'm going to write psi then to be psi I plus psi j, or psi I comma psi j. So I'm just breaking up my random vector of plus minus 1s into 2 parts. And then I'm going to let psi I primed be an independent copy of psi. Okay, and then I do the following rather ingenious trick. So the probability that Q is equal to 0, this, by the law of total probability, is the same as the expected value of the conditional probability that Q of psi, let's now break it up into two parts, psi j is equal to 0, given psi j and the expected value of that. So this internal thing means whatever the random outcome of psi j is, let's fix that. Let's look at the conditional probability this happens for that fixed outcome, and let's average that over all outcomes of psi j. That's just the same thing by the law of total probability. So then by the Cauchy-Schwarz inequality, and now I'm going to run out of space a little bit. Let me write, so by the Cauchy-Schwarz inequality, this is at most the square root of the expected value of the same conditional probability. In fact, maybe I can even copy this. That would be a use of technology. What do I do? Copy and duplicate. So then I square what's inside. I'll take the square root. Okay, this is just the Cauchy-Schwarz inequality. And now the insight is that, so in the world where I condition on psi j, so this event then only depends on psi I. And so I'm looking at the probability this happens squared, which if I want, I can rewrite that in terms of my independent copy of psi I. So let's write that. That is still the expected value of now the joint probability that Q of psi I psi j is equal to 0 and Q of psi I primed psi j is equal to 0. I'm still given psi j. Okay. Yeah, because in the world where I condition on psi j, these two things are independent. This one depends only on psi I, this one depends only on psi I primed. They have the same distribution, so that's just the same as the probability squared. Okay. And well, then I can just use the law of total probability again. That is just the square root of the probability. And let me again use this feature. Okay. Is this clear? Are there any questions about this? So somehow what I've done here is I've used the Cauchy-Schwarz inequality to express this probability I'm interested in terms of a joint probability of two like partially like entangled versions of the same thing. So they're not quite independent copies, but they're like half independent but half dependent. Okay. And what is the good of doing this? Well, if I call this this event here, I'm going to call this star. I observe that, so star certainly implies that the difference between them, if they're both equal to 0, the difference between them is definitely also 0. So minus psi I primed psi j is equal to 0. And then the point is that this thing is a linear, I can interpret it as a linear function of psi j with coefficients that depend on psi I primed. So why is this? Well, let's think about the different terms that appear in this quadratic polynomial. So there are some terms that are like psi I squared, so it's some psi I terms times some other psi I term. There's some terms that are like psi j squared, and there's some mixed terms which have a psi I part and a psi j part. Okay, so the psi j, the terms that are like psi j squared, if it's just a product of two psi j terms, they're going to be exactly the same on this side and on this side. So it's going to cancel out. So I'm going to get no psi j squared terms. I'm going to get some psi I squared terms and some psi I prime squared terms. And I'm going to get some mixed terms. But so if I view these psi I things as being fixed, then in what's left, it's like a linear polynomial. The mixed terms become linear coefficients, and there's no quadratic terms inside J. So this is actually a trick which is also sometimes used in number theory called Weil differencing. It's some very ingenious trick to reduce the degree of what's going on. So what that means is that if I fix outcomes of xi and xi primed, and no longer view them as being random, now I've got a linear function, and so now I can apply the ordinary linear Littlewood-Offord theorem, which I already proved for you earlier, and that'll give me some bound. So this star event happens with probability at most 1 over square root n, because it can be viewed as the probability that a linear thing is equal to 0. And then I take the square root of it, then I get n to the -1/4. So this is how you prove. This is how you prove a weaker bound of n to the -1/4. And I want to write here that the moral is that if I understand the linear Littlewood-Offord problem, that implies that I understand the quadratic Littlewood-Offord problem with a square root loss. So this is something I can do in general. Any kind of quadratic problem I'm interested in, I can convert it to a linear problem with a square root loss. And in fact, I can convert from higher degrees to lower degrees each time I take a square root loss, each time I go down 1 degree. Yeah. Of course, this square root loss is the reason why the original Costello Tao Vu bound is n to the -1/4 instead of n to the -1/2. And so there's been a lot of work in trying to like accept this square root loss, but prove stronger. So there's the ordinary Littlewood-Offord theorem, and there's actually inverse Littlewood-Offord theorems which prove stronger bound under some conditions. And if you can prove a sufficiently strong bound that you can sort of survive the square root loss, then you can sort of treat the complementary case separately. And there's different types of approaches along these lines. But our approach was to somehow not take this square root loss with decoupling, and we call this an inductive decoupling scheme. Okay, so here's how you improve on the basic thing I showed you above. So perhaps, well, I'm going to say one important thing is to perhaps view from a very particular perspective what is happening in this proof up here with star. So this star here is the conjunction of two events. So star, I can rewrite this as, let me copy this. It's the event this is equal to 0, and q of x at j is equal to 0. So yeah, so in going from star to this thing here, what I've lost is I've lost sort of a quadratic part. But if I put that back, these are really the same thing. So the event that this is equal to 0 and this is equal to 0 is the same as the event the difference is equal to 0 and this is equal to 0. Okay, and what is the point of this? Well, so what I've done in going from here to here is I've completely ignored this quadratic part. So I've sort of dropped. So the problem was really about two equations. It was about this equation and this equation. I've dropped one of the equations, and I sort of expect each of them to independently hold with probably 1 over square root n. And I've sort of dropped them, and now I get 1 over square root n. And so I want to say here what happened is that half the problem is quadratic, so there's like a linear part and a quadratic part. Half the problem is quadratic. We ignored the quadratic part. And so the resulting exponent is half as good as it should be. This is one way to interpret what has just happened in this decoupling proof. Okay. So with this point of view in mind, perhaps something that I should try and do is, so here I've reduced like this application of Cauchy-Schwarz, this thing that I was interested in, I reduced that to a pair of equations. Half of those equations were quadratic. It would have been good if I could reduce it to like 10 equations, and like 9 out of 10 were linear, and only one was quadratic. So somehow I want to view decoupling as like reducing the proportion of my problem which is quadratic. So in general, I want to get a whole system of equations, and I want most of those to be linear. So throwing away the quadratic part is not going to cost me very much, because I never know what to do with the quadratic part. Okay. And so the way that we do this is just by decoupling multiple times. So the idea is to decouple again. So once we've got to this stage, so we're already, we're sort of viewing xi I and xi I prime as constant. So the only randomness remaining is in xi j. I then want to split xi j into two parts. So choose a partition. So j should be I2 union j2. And I want to make an independent copy. Say I2 primed of xi I2. So I want to do exactly the same thing I did before, but sort of in this restricted world where I'm only looking at the j part of the problem, which is the only part that's still random. And so then I obtain 4 equations. So I have this equation. This equation now becomes 2 equations. It's like this versus an independent copy of itself. And this becomes 2 equations. It's this versus an independent copy of itself. And then the key observation is that I can, and this is perhaps not so obvious, that I can take these 4 equations and I can manipulate them in a comparable way that I've manipulated the 2 equations. And so manipulate so that 3 are linear. So there is a way to do sort of linear operations on these 4 equations in such a way that I get 3 linear equations and 1 quadratic equation. So now sort of 3/4 of the problem is quadratic, and throwing away the quadratic part won't cost me as much. Yeah. So just if I have, okay, I don't really have time, so maybe
but maybe one question. So you should also be careful doing this, that every time you get a linear equation, there would be many non-zero terms. So you should look
this is really crucial. And in fact, so this is just one of many non-degeneracy conditions I need. In general, if I have a system of linear equations, and I want to prove that the whole system is equal to 0, is roughly the product of the probabilities they're each equal to 0, I need these to be sort of independent linear equations, like linearly independent equations. Because if I had 10 copies of the same equation, of course, I gain nothing from that. So not only do I need the coefficients to not be 0, but I need like the vectors describing these linear equations to be sort of robustly linearly independent. So in fact, that's not all I need. There's multiple different non-degeneracy conditions that I need throughout this proof. And I need to sort of, as I'm going through this proof, I need to maintain that they each likely to hold. And this is actually the main reason why we're having trouble generalizing this to higher than quadratic. Just because in general, you're going to convert one equation into many equations 1 degree lower. And we do have techniques to get our hands on large systems of linear equations. I mean, linear equations are just much easier things to understand. Like linear independence is the correct thing to describe when these things are independent. And that becomes a lot more difficult with higher degrees. But yes, this is definitely something we need to take into account. And of course, in the proof of all these non-degeneracy things, we need to somehow use this assumption that we've made that you can't fix S variables to fix the value of the polynomial. This is really the only non-degeneracy condition that we need, that we have to ensure that what is going on through the whole proof makes sense. Anyway, but so I'm sort of running out of time, but let me quickly write the punchline. So now a quarter of the problem is quadratic. So if I stopped here, I would get a bound not not n to the 1/4, but n to the -3/8, so closer to n to the 1/2, because I've thrown away less of the problem. In general, if I decouple k times, then I get a bound that looks like n to the -1/2 plus 1/2 to the k plus 1. So each time I double the number of equations, and okay, it's sort of lying a bit to say that all but one of them are linear. It's really a little bit more complicated than that. There's some weighted aspect going on, and also you sort of, things are linear in different parts. Like you've got the I and the J and the I prime and the I1 and the I2 and the J2 and the I3 and the J3, and things are linear in different parts of these. But let me, for simplicity, say that all but one of those are all but one of my exponentially many equations are linear, and therefore I get a bound that looks like this. And so then I just do this k equal log n times. So if I do this log n times, then this part of the exponent will be so insignificant, it'll be 1/2 to the log n, which is 1/n. So n to the 1/n is just a constant. If I do this whole procedure log n times, then the throwing away the quadratic part of this huge system of linear equations will only cost me a constant factor in the final bound, and that is at an extremely high level, skipping a huge amount of steps. That's sort of the approach that we had to this problem. Yeah, so I've completely skipped over. I now have systems of linear equations. We need new technology to study anti-concentration of systems of linear equations. There's a whole bunch of other stuff there. But I think this type of general scheme is hopefully applicable to other types of problems as well, and I think it's sort of the main insight in what we have done. So maybe let me stop here. Thanks.
Okay, so thank you, Mathew, for a great talk. Really very clear and very entertaining. So let me kind of invite everybody now to unmute yourself if you have questions, and yeah, we can ask Mathew for more details. Any questions? Because I asked all the questions while Mathew was doing it.
I have a question. So every time you do the splitting, you also have the number of variables. So it seems like after you split log n times, you'll end up with like little o of n variables, or like n over some polylog.
If I split log n times, I'd definitely be in trouble, because then each part would have like a constant number of variables in it. So this is not true forever, but it is true. Like it is okay for log n, and this is not trivially true. You need to be very careful about how you do the split at each point. Like I wrote at the start that you split into like I has 1/2 and J has 1/2. You really shouldn't do that. You should make sure that the sort of active part, like it should be like 1/k versus 1 minus 1/k. Really 1/k squared times 1 minus 1/k squared. The point there is that 1/k converges, the sum of 1/k converges. So the part where all the action is happening, the J part, that should never shrink to 0. Like that should always remain at least 0.1 of the variables. So that's the key idea there. Yeah, I think I had the same when we were first working through this. I had the same impression that like this seems to work up to a constant, but when you start letting k go to infinity, you run into some issues. But somehow it worked.
Thanks.
More questions?
I can ask a question. So, hi, Matt. Thanks for the lovely talk. So when you try to generalize this to higher order polynomials, is it that it becomes like, are there any fundamental obstacles in what you're trying to do, or is it just becomes really difficult to implement?
So I don't think there's fundamental obstacles. Like at the resolution that I showed you, everything makes sense. The problem is that so Benny pointed out one type of non-degeneracy that you need to take care of. There are actually others. Can you hear me? Everyone's frozen for me.
Yeah, no, we hear you.
Hello?
Hello, we hear you, Mathew.
Okay, everyone frozen. Yeah, sorry, I was saying, yeah, so there's these like non-degeneracies conditions that you need to maintain through the whole process. Unfortunately, it seems that for higher degrees, these non-degeneracy conditions, like showing that those are unlikely, is not necessarily easier than the problem you started with. So you have to really, I think it makes sense to think about this in geometric terms. Like this decoupling, it's like really taking the intersection of two translates of the same variety, and you're like worried about the translate this intersection of two translates not being like a lower dimensional object or something like that. And like expressing that as another polynomial anti-concentration problem, the degree of that polynomial anti-concentration is not lower than the degree you started with, which I don't think this is fundamental. I think this is just a question of like doing the induction in the right way that things. So I really don't think it's fundamental, but I think it's definitely going to become a lot more complicated just because everything is so obvious in the linear case. Like in the quadratic case, all the difficult parts are linear somehow. Like the intersections of things are linear, and you can just stare at things and see what's going on. And it's a different matter for higher degrees. Yeah.
Okay, so I think maybe let's stop here. So thanks, Matt, again. A lovely talk. We can stop recording.